Welcome to our online chemistry class. Our topic is coordination compound. Let us discuss theories of bonding in complexes. In that, we have to discuss first theory, that is valence bond theory. So, bonding in coordination compound. Werner was the first to discuss the bonding features in coordination compounds. There are many theories which can explain the nature of bonding as well as various properties of coordination compounds. And which are the different theories? First one is valence bond theory, second is crystal field theory, third is ligand field theory, and fourth one is molecular orbital theory. So let us discuss first theory in detail. There are some postulates of this theory or assumptions. Let us discuss one by one. So valence bond theory was developed by Linus Pauling. This theory accounts for coordinate bond. So what is the meaning of this coordinate bond that we discuss first? So all are familiar with covalent bond. Covalent bond is nothing but mutual sharing of one or more electrons to form a bond between two atoms, that is covalent bond. So in covalent bond, both the bonded atoms share electrons, one or more. So here in coordinate bond, there is also a sharing, but both the atom does not share electrons. Only one atom shares a pair of electrons or non-bonding pair of electrons. And that atom is donor, while the another atom which participate in bond formation, which accept that non-bonding pair of electron, that is called as acceptor. And the bond between donor and acceptor is called as coordinate bond. So coordinate bond formation due to overlap of vacant hybrid orbital of central metal atom. So it acts as a acceptor with filled orbital of ligand which acts as a donor, each containing lone pair of electrons. The central metal ion present in the complex provides a definite number of vacant orbitals S, P, D for the formation of coordinate bonds with ligand. So here we consider the transition metal, so D orbital can also be involved to form bond with ligand. Then each ligand has at least one orbital containing a lone pair of electrons. For example, in case of ammonia, nitrogen contain one lone pair of electron. In case of water, oxygen contain two lone pair of electrons, that is non-bonding pair of electrons. The number of vacant hybrid orbitals formed is equal to number of ligand donor atoms surrounding the metal ion, which equals the coordination number of metal. So for example, if we consider CONH3 6 times 3 plus ion, in this ion there are 6 ammonia molecules, so ligand number is 6, so number of vacant hybrid orbital formed is also equal to 6. Okay, and that is the coordination number of cobalt. Then overlap between the vacant hybrid orbitals of metal and the filled orbital of the ligand leads to formation of metal ligand coordinate bond. Metal acts as an acceptor, ligand acts as a lone pair donor. Then the hybrid orbitals used for the metal ion point in the direction of ligand. So here hybrid orbital word is used, that means that central metal atom undergo a process of hybridization, and here atomic orbital undergo hybridization, and newly produced orbitals are called as hybrid orbital. Then the n-1d or nd orbitals used in hybridization allow the complex to be classified as first outer orbital complex and second one is inner orbital complex. So why these words are used, let us discuss. For hybridization in the outer orbital complex, for example, in case of transition metals, the first series is 3D series from scandium to zinc, and in this series the elements are placed in fourth period. So valence shell, outer shell is fourth shell, and the inner shell is 3D. 3D orbital is involved, then the complex is called as inner orbital complex. So orbital is n-1d because these elements are fourth period elements. And if 4D orbital is involved, then it is called as outer orbital complex. So I think you have understood why the word is outer orbital and inner orbital complex. Then type of hybridization decides the structure of complex or geometry of that complex. So there are different types of hybridization. Let us see one by one. The type of hybridization, coordination number, and geometry of the complex. So first type is sp, means 1s and 1p atomic orbital of that central metal atom undergo a process of mixing and recasting. So two atomic orbitals are involved. So the coordination number is 2, and these two orbitals are placed linearly. So geometry of the orbital and structure or geometry of the complex is also linear, because at that linear position there is a minimum repulsion between two atomic orbitals and maximum symmetry and definite orientation. If 1s and 2p orbitals are involved, means total 3 orbitals are involved, so coordination number of that central metal atom is 3. These 3 orbitals can place with maximum symmetry, minimum repulsion in triangular shape. So geometry of the orbital and complex is triangular. If 1s 3p atomic orbitals are involved, means total 4. These 4 sp3 hybrid orbitals take a position of tetrahedral. So all are familiar with this. For example, all of you know about the methane. So tetrahedral is the shape. Then 1d, 1s and 2p atomic orbitals are involved, means total 4 again. So initially also we discussed 4, then geometry is tetrahedral. Here also 4, but geometry is square planar, because here instead of 1p, 1d orbital is involved, and that is n-1d. If n-1d, s and p, 3 type of p atomic orbitals of outer shell are involved, means total 5 atomic orbitals undergo a hybridization. Coordination number central metal atom is 5. The geometry of the orbital is triangular bipyramid. Then n-1 type of 2d orbitals, 1s and 3p atomic orbitals, that is outer orbitals, means total 6. The geometry is octahedral. Then if, and here also we can write sp3d2, means s 3p and 2d of outer orbitals also involved, then same is the coordination number 6 and geometry is also octahedral. Then if 3 inner d type of orbital, 1s and 3p outer orbitals involved, then total 7 orbitals are involved, then geometry is pentagonal bipyramid. Then let us see detail about this with example. Then the geometrical shape of the complex ion depends on the hybridization of metal ion. Okay, so same is the shape of that hybrid orbitals for the complex. Then coordination bond or coordinate bond is stronger if overlapping between the orbital is greater. If n minus 1 d, so here if you consider post transition series 3d orbitals are used for hybridization, complex are called as inner complex. If 4d atomic orbitals are used for hybridization, then that complex is called as outer complex. So in your syllabus only post transition series elements are and their complexes are involved. So you can write here n minus 1 means 3d and nd means 4d. When strong field ligand like NS3, cyanide are involved in the formation of complex, they cause pairing of electron present in the metal ion before hybridization, and this process is called as spin pairing. So what is this spin pairing? We will discuss while discussing the example. So let us see the formation of octahedral complex with first example CONH3 6 times 3 plus with low spin. So what is the name? There are 6 NH3. So hexamine, your ammonia is neutral, so this overall charge on the complex is the oxidation state of cobalt, so cobalt is 3 plus. So what is the name? Hexamine cobalt 3 ion. So oxidation state of cobalt is 3 plus. So atom, it is atomic number 27. So it is very easy to write the electronic configuration of first transition series from 21 to 30. According to its atomic number you can easily write, except chromium and copper. So cobalt atomic number 27. So write down that 2 electron in 4s and 7 electron in 3d. Before that you have to write the inert gas, that is argon. So electronic configuration of cobalt is argon 4s2 3d7. Okay, when this cobalt atom donate 3 electrons, out of that 2 electrons are donated from its 4s orbital and 1 electron is donated from 3d orbital, then electronic configuration become argon 3d6 4s0. Okay, 4p is already 0. So this is the electronic configuration of cobalt. Before this write down argon. Okay, then number of amine ligand is equal to 6. Therefore number of vacant metal ion orbital required for bonding with this ligand must be 6. But if you observe this electronic configuration, there are only 4 vacant orbital. So we want 2 more vacant orbital, and for that purpose, as your complex is low spin, so pairing of electron will take place before hybridization. So these 2 electron from 3d orbital undergo pairing with these 2 electron, and after pairing the electronic configuration would be like this. So now if you observe this electronic configuration, don't forget to write R1 here. Now 6 vacant orbital, and so we require 6 vacant orbital because 6 ligands are there. So the 6 ligand means NH3 molecule donate 6 lone pair of electron towards the cobalt. Before that, this cobalt undergo hybridization because the energy of 3d, 4s and 4p orbital is totally different, but all the bonds in the complex CONH3 bond, that is CON bond in NH3, are identical, but energy will be different if before hybridization they undergo bonding. So that's why they undergo hybridization. All the bonds should be equivalent. So that you already learned in last year. So what is the hybridization? Two 3d orbital, one 4s orbital and 4 p orbital. So here which d orbital is involved? 3d. Here last lay 4th and n minus 1 d, that is 3d orbital involved. So it is a inner complex. Okay. So here hybridization is d2sp3. Okay. So two 3d orbital, one 4s and 3 4p orbitals. So orbital for hybridization are decided from the number of amine ligand, which is 6. So here complex is low spin complex and inner complex. And when ligand donate the 6 lone pair by 6 different nitrogen of ammonia molecule, then your electronic configuration after complex formation will be like this. So if you observe this electronic configuration, all the electrons are paired, so complex is dimagnetic in nature. And here is the structure. Structure is octahedral. Okay. Now let us discuss another example. So COF6 3 minus, but spin is high spin. So hexafluoro cobaltate and one fluorine is 1 minus, so 6 fluorine carrying 6 minus charge. So x minus 6 is equal to minus 3. So cobalt is x is equal to plus 3. So oxidation state of cobalt is plus 3. Okay. Now atomic number of cobalt is 27. So electronic configuration of cobalt atom is argon 4s2 3d7. Okay. So when this cobalt atom donate 3 electron, then it forms cobalt ion CO3 plus. So the electronic configuration of cobalt 3 plus become argon, 2 electrons from 4s and 1 from 3d will be removed. So 3d contain only 6 electron, 4s contain 0 electron. So electronic configuration is argon 3d6, 4s 0, 4p 0. Now there are 6 fluoride ion in your complex which acts as a ligand. So thus the number of vacant metal ion orbital required for bonding with this fluoride ligand would be 6. But if you observe this electronic configuration, there are only 4 vacant orbital from outer shell, that is 4th shell. So as your complex is of high spin, that means pairing of electron will not take place before hybridization. So the electronic configuration of CO3 plus ion remains same in the free state as shown above. So but we require 6 vacant orbital. So the 6 orbital available for hybridization is cobalt electronic configuration 1 4s and 3p 4p are available. So next to that is 4d orbital, because there is no pairing in 3d orbital. So there are 5 4d orbitals which are available, but already 4 are from 1 4s and 3 4p. So it requires only 2 orbitals from 4d. So these are the orbitals available: 1 4s, 3 4p and 2 4p. So what is the hybridization? It is not D2sp3 like your previous complex. but it is sp3d2. Now outer d orbital is involved in hybridization, so it is outer complex, and previous one is inner complex. Okay, so 6 metal orbitals after bonding with 6 fluoride ligand leads to sp3d2 hybridization, and the d orbital participate in the hybridization for this complex is 4d. The 6 vacant sp3d2 hybrid orbital of CO3 plus overlap with 6 orbital of fluoride ion, forming 6 number of COF coordinate bond. And when that 6 fluoride ion donate their 6 lone pair of electron to cobalt 3 plus ion, then electronic configuration of that complex is like this. 3d contain 6 electron, 4s contain 2, 4p contain 6, and 4d contain 4. Okay, but if you observe here, 3d contain 4 unpaired electron and remaining electrons are paired. So as there is an unpaired electrons, your complex is paramagnetic in nature. And as the hybridization is sp3d2, the structure is octahedral. In previous case, it is d2sp3, geometry is remain same, that is octahedral. But if it is d2sp3, that is inner complex, and this is sp3d2, so it is outer complex. That is the difference. Then let us see the next example, formation of tetrahedral complex, and first one is NiCl4 2 minus. Here is the correction, it should be 2 minus, because Cl is 1 minus, so there are 4 minus charge for the ligand, and Ni is 2 plus, so overall charge on the complex is 2 minus. So Ni atomic number 28, so electronic configuration is argon 4s2 3d8. As Ni is 2 plus, because x plus minus 4 is equal to minus 2, so x become plus 2, so it should donate 2 electron. So if Ni donate 2 electron, it gives Ni 2 plus, so electronic configuration become 2 electron from 4s will be removed and 8 electron from 3d remain as it is. So electronic configuration of Ni2 plus is argon 3d8 4s0 4p0. As the number of chloride ligand is 4, there should be 4 vacant metal ion orbital for bonding with this chloride ligand. So here 4 orbitals are already available for hybridization, and they are 1 4s and 3 4p. The complex is tetrahedral. The 4 metal ion orbital for bonding with Cl minus ligand are derived from sp3 hybridization, and the 4 vacant sp3 hybrid orbital of Ni2 plus overlap with 4 orbitals of chloride ion to give this NiCl4 2 minus complex. And what is the electronic configuration of that complex? When these 4 Cl minus ion donate 4 lone pair to Ni2 plus, the electronic configuration is like this: 3d 8 4s2 4p6. Okay, if you observe the electronic configuration, there are 2 unpaired electrons So here also one correction. Here let write 2. Here 2 unpaired electrons are present. So the complex is paramagnetic in nature, and tetrahedral geometry of this complex is like this: NiCl4 2 minus, which is similar to your methane. Now next complex is square planar complex. Example is NiCn4 2 minus. So again nickel is the central metal element. So all are familiar with the atomic number of nickel. It is 28. So electronic configuration is argon 4s2 3d8. Here cyanide ligand carrying -1 charge. So what is the oxidation state of nickel? Is X -4 is equal to -2. So X become +2. So that is the oxidation state of nickel. So when nickel atom donate 2 electrons, it will give Ni2 plus. That 2 electrons are donated from 4s. So electronic configuration of Ni2 plus is argon 3d8 4s0 4p0. As the number of ligand, that is Cn minus, are 4, the number of vacant metal ion orbital required for bonding with this 4 Cn minus ligand would be 4. The complex is square planar. Okay, it is already mentioned, but if you observe the previous example, there are also 4 Cl minus, but that nickel undergo tetrahedral shape or tetrahedral structure because hybridization is sp3. So here also 1s3p orbitals are involved. So one question may be in your mind, why it does not undergo tetrahedral shape? Why the hybridization is different? Why it is not sp3? So this explanation is not given by this theory. So this is the limitation of this theory. So as complex is square planar and sp3 hybridization does not show square planar geometry, it shows dsp2 hybridization. If dsp2 is the hybridization, geometry is square planar. If sp3 is the hybridization, geometry is tetrahedral. Okay, so that is the limitation. We will discuss that limitation in our next video while discussing the crystal field theory. So as complex is square planar, so Ni2 plus ion undergo dsp2 hybrid orbitals, but their d orbital contains 2 unpaired electrons, so there must be spin pairing. Okay, so 3d electrons are paired before the hybridization, and the electronic configuration of Ni2 plus become, so electronic configuration remains same, only unpaired electron becomes paired, and there is availability of one vacant d orbital, that is 3d orbital. So now 1d, 1s and 2p orbitals are undergo dsp2 hybridization, and these 4 vacant dsp2 hybrid orbitals of nickel overlap with 4 orbitals of cyanide ion, which is a ligand, to form 4 NiCn coordinate bond. So here nickel carbon bond is formed. Okay, and when that 4 Cn minus ion donate 4 lone pair of electron, then the electronic configuration of complex would be like this, and hybridization is dsp2. So structure is square planar. If you observe the electronic configuration, there is a no unpaired electron, so your complex is diamagnetic in nature, it is not paramagnetic. Okay, so always mention the hybridization and magnetic behavior. Okay, then limitation of VBT. So valence bond theory does not explain high spin and low spin nature of the complexes. In other words, strong field and weak field nature of the ligand cannot be distinguished. Then it does not provide any explanation for the color of coordination bond. So while discussing all these examples, it doesn't mention the color. Then structure of the complex predicted from the VBT would not always match necessarily with those determined from the experiments. So if there are 4 ligands in your complex, geometry is tetrahedral or sphere planar, sometimes that explanation provided by this VBT cannot be matched with experiments. Then there are 2 more limitations. So this theory does not explain about the interpretation of thermodynamic and kinetic stability of the coordination compound, whether that compound is thermodynamically stable, kinetically stable. This explanation is not given by this theory. Then one more is this: if coordination number of central metal atom is 4, then whether that complex is tetrahedral or square planar, that also cannot be explained by this theory. Then at the end of every complex, we predict about the magnetic behavior, paramagnetic, diamagnetic. The explanation regarding the experimental condition or experimental explanation cannot be explained by this VBT. So these are some limitations of VBT. To overcome these difficulties in VBT, the crystal field theory has been proposed and which was widely been accepted. So we have to discuss this crystal field theory in our next video. So thank you for watching my YouTube channel Mukesh KHARGE.